Let me ask you something simple. Open your freezer, reach in there, and grab an ice cube. Hold it up to the light. What do you see? You see right through it. Maybe a little distortion, maybe a milky cloud in the middle where some bubbles got trapped, but mostly you can read the back of a cereal box through a clean chunk of ice. Light goes right in one side, comes right out the other, no problem. Now put on a coat and walk outside on a winter day. Bend down, scoop up a handful of snow. Look at it. White. Brilliant, blinding white. So white that on a clear morning, with the sun on a fresh snowfield, you have to shield your eyes or you get a headache. People go snowblind staring at it. Now here is the thing that ought to bother you. Those two things in your hands are made of the same stuff. The same molecule. 2 hydrogens, 1 oxygen. Same chemistry, same atoms, same crystal, same everything. One of them is as clear as a window. The other one is whiter than a fresh sheet of paper. And nobody added anything. Nobody dyed the snow. Nobody bleached it. It is just water. Frozen water. So how can the same substance look completely different depending on whether you crush it up or leave it in a chunk? That is the puzzle. And once you understand the answer, you start seeing the same trick everywhere. In your sugar bowl, in your salt shaker, on the head of a beer, in the clouds over your house, on the back of a polar bear. The world is full of this trick, and most people walk past it every day without noticing. So let me ask you the obvious starter question. What does it mean for something to be white? Forget snow for a minute. Just think about white. Take a piece of paper. Why is it white? White is not really a color, you know. Not in the same way that red or blue or green are colors. Red light has a specific wavelength. Blue light has a specific wavelength. But white light, the light coming out of the sun, the light coming out of a flashlight, that light is a mixture. It contains all the colors at once. Red, orange, yellow, green, blue, violet, all together. If you send white light through a prism, the prism separates them, fans them out into a rainbow, and you see what was always there. White light is the whole orchestra playing at the same time. So when something looks white, what is happening? It means that whatever you are looking at is sending all those colors back to your eye equally, all together. It is not picking favorites. The red light hits it, the red light bounces off. The blue light hits it, the blue light bounces off. Same for green, yellow, violet, the whole bunch. Nothing gets absorbed, nothing gets held back. Everything comes out just the way it went in, but pointed back at you. Compare that to a red apple. A red apple takes the white light from the sun, and it gobbles up the green and the blue, swallows them, turns them into a tiny bit of heat, and sends only the red light back. That is why it looks red. Not because there is red in it, but because the green and blue have been removed. White means nothing was removed. All right, hold on to that thought. Now flip it around and ask, what does it mean for something to be transparent? An ice cube, a pane of glass, a glass of water. What is the deal there? Transparent means the light goes through. It does not bounce back. It does not get absorbed. It just passes from one side of the object to the other, comes out a little bent, maybe a little slowed down, but otherwise unchanged. Your eye catches the light from whatever is on the other side, and so you see through. Now here is something that took people a long time to figure out. Why does light pass through some things and not others? Why can it sail through a window but not through a wall? They are both solid. They are both made of atoms. What is different? The answer has to do with what light is, and what atoms are doing when light hits them. Light is a wiggling electric field. As it passes by an atom, the electric field grabs the electrons in that atom and shakes them. The electrons start to wiggle, and here is the deal. Atoms have certain natural frequencies they like to wiggle at, the same way a bell has a certain note it likes to ring at. Or a wine glass has a certain tone it sings when you run a wet finger around the rim. If the light coming in matches one of those natural frequencies, the electrons start ringing like a bell, and they swallow up the energy of that light. The light is gone, absorbed. turned into wiggling electrons, eventually heat. That is why a wall is opaque. The atoms in the wall have natural frequencies that match visible light, and so they grab the visible light and eat it. But if the light coming in does not match any of those natural frequencies, then something else happens. The electrons do shake a little bit, but only a little. And they do not absorb the light. They just pass it along. The light goes through, slightly slowed, slightly bent, but mostly intact. Water, frozen or liquid, happens to be one of those substances whose natural frequencies do not match visible light. The water molecule has all its action up in the ultraviolet, and a little bit down in the infrared, but right in the middle, where our eyes work, the molecule is silent. It does not absorb red, it does not absorb blue, it does not absorb anything you can see. Light just sails through. So that is why an ice cube is clear. The water molecules in it do not eat the light. They let it pass. But now, you see, the puzzle gets worse. Because if water does not absorb visible light, then snow should not absorb visible light either. They are the same molecule, the same atoms doing the same thing. The light should sail straight through a snowflake, just like it sails straight through an ice cube. So why on earth is the snow white? This is where you have to start being careful. Because the easy answer is wrong. The easy answer is to say, well, snow is more like fluffy stuff and ice is more like a solid, and somehow that explains it. But that does not explain anything. You have just renamed the problem. You said it is fluffy. So what? Why does fluffy mean white? Let me show you what is really going on. But I have to add one piece first. Pour yourself a glass of water and stick a pencil in it. Look at the pencil from the side. The pencil looks broken. The part above the water and the part below the water do not line up. The part underwater looks like it has been shifted sideways. We have all seen this since we were children. We do not even think about it anymore. What is happening is that light travels at different speeds in different materials. In empty air, light goes at its top speed, the famous 186,000 miles per second. But the moment it hits water, it slows down. In water, light only goes about 3/4 as fast. In ice, almost the same. About 3/4 the speed of empty space. When light slows down, going from one material into another, it bends. It is sort of like a car driving from a paved road onto a muddy field at an angle. One wheel hits the mud first. That wheel slows down, the other wheel is still going fast on the pavement, and the car turns. Light does the same thing at a boundary. It turns. We have a number we use to describe this slowing down, and it is called the refractive index. The refractive index of empty air is just 1. The refractive index of water is about 1.33. The refractive index of ice is about 1.31. Glass is around 1.5. Diamond is 2.4. The bigger the number, the more the light slows down, and the more it bends. Now here is the thing that nobody tells you in school. Every time light crosses one of these boundaries, even when it does not get absorbed, even when the material is perfectly transparent, a little bit of the light bounces back. Some of it goes through, but some of it reflects. You can see this yourself. Look at a window at night with the lights on inside. You see a faint reflection of yourself in the glass, even though the glass is transparent. The glass is letting most of the light through, but a small fraction, around 4%, is bouncing back. That is why you see your reflection. This is just a fact about how light deals with boundaries between different materials. Whenever light hits a place where the speed changes, some of the light keeps going and some of it bounces. The amount that bounces depends on how big the speed difference is. Air to glass, about 4% reflects. Air to water, about 2%. Air to ice, around 3%. Most of the light goes through, but not all. All right. Now we have all the pieces. Now I can show you the trick. Take that ice cube again. It is one solid chunk. Light comes in the front face. Tiny bit reflects off the front face. Most of it goes through. It crosses the inside of the ice cube without hitting any boundaries. It hits the back face. Tiny bit reflects off the back face. Most of it goes out the other side. So in total, Light went into the front, came out the back, lost only a few % along the way. Your eye, looking through the cube, sees the light from whatever is on the other side. The cube is clear. The cube is transparent. Now take that same ice cube, set it on a table, and smack it with a hammer. Crush it. Smash it into a pile of tiny shards. Tiny grains. Now look at the pile of shards. What do you see? You see white. A heap of crushed ice is white, or near enough to white that you would say it is white. We have just turned a transparent block into a white powder, and we did nothing to the chemistry. We only changed the geometry. Why did this happen? Because now the light, instead of going through one front face and one back face, has to deal with thousands of faces, millions of faces. Every shard of ice is a little crystal, and every crystal has surfaces, and every surface is a boundary between ice and air. And at every single one of those boundaries, the light bounces a little, refracts a little, splits up a little. The light enters the pile from above, and it hits the first shard, and a little bit reflects, and a little bit refracts and goes inside that shard, and then it hits the back of that shard, and a little bit reflects again, and a little bit refracts out into the air on the other side, and now it hits the next shard, and the next, and the next. The light is bouncing around inside the pile of crushed ice like a pinball machine, getting kicked from one surface to another, splitting into smaller and smaller pieces, going every which way. And here is the key. After enough of these bounces, the light has lost track of where it came from. It came in pointing one direction, and now it is pointing every direction. Some of it has bounced its way back out the top, but spread out, scattered, smeared into all angles. From your eye looking down at the pile, light is coming back at you from every grain, from every surface, from every angle. The pile is sending light back, but not in a flat sheet like a mirror. It is sending light back in a hopeless tangle. That is what we mean by diffuse reflection. The light is coming back, but the original direction is gone. And because all the colors do this equally, because red light and blue light and green light all bounce off these boundaries the same way, all the colors come back at your eye in equal amounts. And what do you see when all colors come back at you in equal amounts? You see white. Snow is exactly the same thing. Snow is just a fluffy pile of tiny ice crystals separated by air. Trillions of little boundaries between ice and air, each one reflecting and refracting the light a little bit. Light enters the snowbank, gets kicked around, splits up, scatters, and a good fraction of it eventually bounces back out into your eyes. From every direction. All colors equally. White. So the real difference between an ice cube and a snowdrift is not chemistry. It is not the molecules. The molecules are doing exactly the same thing in both cases, which is mostly nothing. They are just sitting there, letting the light pass through. The difference is the number of boundaries. One boundary on each side, you get a clear cube. A million boundaries, you get a white pile. Now I want to stop here for a moment and let that sink in, because it is a strange thing if you think about it. We are taught from a young age that the color of a thing is a property of the thing. The grass is green. The sky is blue. The snow is white. As if the color is in the material, baked in, fundamental. But it is not. The color sometimes is a property of the arrangement. You can take a clear, colorless substance, and just by chopping it up small enough, you can make it look white. You did not change what it was. You changed how it was put together. This sounds like a small thing, but it is actually a big idea, and we are going to come back to it. For now, let me push you a little further. Why white, specifically? Why not some other color? When light bounces off all those boundaries inside the snow, why does it come out as the same balanced mix of colors that went in? Why does it not get tinted along the way? Here is why. The amount of light that reflects at one of these boundaries depends on the difference in refractive index between the two sides. Ice on one side, air on the other. That number, the difference, does not change very much as you go from red light to blue light. It is almost the same for every color. So at every bounce, all colors reflect by about the same amount. Red bounces equally. Blue bounces equally. Green bounces equally. And so after thousands of bounces, the light coming back out of the snowbank is still the same mix as the light that went in. Whatever color the sunlight was, the snow sends it back. White light in, white light out. This is different from what happens with very small particles, by the way. If you make the scattering particles much smaller than the wavelength of light, then suddenly the colors do start to behave differently. Blue light bounces off small things much more than red light does. That is why the sky is blue. The molecules of nitrogen and oxygen up in the atmosphere are way smaller than a wavelength of light, and so they kick the blue light around far more than they kick the red light. The blue gets scattered down to your eyes from every direction in the sky. The red mostly goes straight through. So you see a blue sky and a red sunset. But snow grains are not tiny like that. A typical snowflake might be a millimeter across, and even a single ice crystal in fresh powder is much bigger than the wavelength of light. The wavelengths of visible light are around half a micron, which is 1/2000th of a millimeter. So a snow grain is enormous compared to the light bouncing inside it. At those sizes, all the colors scatter the same. White in, white out. This is why a glass of clear water poured into a blender with some air comes out as white foam. The water did not change. The air did not change. You just made a billion little bubbles, a billion little boundaries between water and air. The same trick. Clear plus structure equals white. It is why a single grain of salt, if you look at it closely, is a perfect transparent crystal. But a salt shaker full of salt is white. Each grain is clear. The pile is white. Same for sugar. A single sugar crystal, like rock candy, is clear. A bowl of granulated sugar is white. Crush a piece of glass, and it goes from clear to a white powder. Take a sheet of clear plastic and rough up the surface with sandpaper, and it turns frosty white. The clouds in the sky, every one of them, are made of either tiny water droplets or tiny ice crystals, both of which are individually transparent. The cloud is white because of the structure. Polar bears, here is a good one. Polar bear fur is not actually white. Each strand of polar bear fur is a hollow, transparent tube. Clear, colorless. But there are many millions of these tubes packed together on the bear, and the air-keratin boundaries scatter the light, and so the bear looks white. The bear's skin underneath is actually black, to absorb whatever heat manages to get through. Black skin, transparent fur, white-looking animal. The same trick. The foam on top of a beer. The beer underneath is yellow, transparent. The foam on top is white. Same liquid, just full of tiny bubbles. The spray at the bottom of a waterfall. The river is clear water. The mist at the base, where the water has been broken up into countless droplets, is bright white. Once you see this, you cannot stop seeing it. Everywhere you look in nature, when something clear gets broken into pieces and mixed with air, the result is white. It is one of those simple truths that explains 1,000 observations. All right. Let me throw a wrench in this for a moment. Because if everything I just said is true, we have a problem. If snow is just clear ice with lots of boundaries, then snow should always look white. But it does not always look white. Have you ever looked deep into a glacier? Or seen those photos of crevasses in Antarctica? Or icebergs in the ocean? The deep inside of those things is blue. Sometimes a really intense, pale, beautiful blue. So if all of this is just about boundaries and white scattering, where does the blue come from? Here is the answer, and it is very nice. I told you earlier that water does not absorb visible light. That is almost true. It is mostly true, but it is not exactly true. Water absorbs visible light a tiny, tiny bit, especially at the red end of the spectrum. Just a smidge. If you have 1 inch of water in front of you, you cannot tell. Even if you have 10 inches, 20 inches, 100 inches, the absorption is still so weak you would say the water is colorless. But if you have, say, 10 meters of water, or 50 meters, or 200 meters, that tiny bit of absorption starts to add up. The red light gets eaten away, little by little, mile by mile. The blue light keeps going. So if you have a glacier that is hundreds of feet thick and light tries to pass through it, the red part of the light gets absorbed along the way and only the blue part survives. When that blue light eventually scatters back to your eye, it has been filtered. You see blue. That is why deep ice looks blue. That is why the inside of a crevasse looks blue. That is why a thick chunk of glacier ice can have a color even though a small chunk would not. It is also why the deep ocean is blue, by the way. Same reason. Long path through water, red gets absorbed, blue survives. Now you might be wondering, well, why is fresh snow not blue? It has tons of ice in it. The answer is that in snow, the light does not travel through that much ice. It bounces off of surfaces and gets reflected back out before it goes very far. The total path length through the ice is short. So the absorption is too small to matter, and you get white. But in a solid glacier, the light has to travel a long way before it finally finds a boundary that sends it back. And during that long journey, the red gets eaten. So now we have two phenomena from the same atoms. White from snow, because of countless tiny boundaries with no time for absorption to matter. Blue from glaciers because of long path lengths that allow tiny absorption to add up. Same molecule, same chemistry, different appearances depending on geometry. I want to take a deep breath here because I want to point out something important. We have been doing physics, light, scattering, refraction, absorption, all of that. But what we have actually been doing is much more general than physics. We have been showing how the same building blocks can produce wildly different appearances depending on how you put them together. We have been showing how complexity emerges from arrangement. Think about it. A water molecule is the same in steam, in liquid water, in ice, in snow, in a cloud, in a glacier. The molecule does not know what context it is in. It does not know it is supposed to be white when it is in snow and clear when it is in a cube. It is just sitting there, being a water molecule, doing the same thing it always does, which is wiggle a little bit and refuse to absorb visible light. But the world we see, the world of white snow and clear ice and blue glaciers and gray clouds and white foam and falling rain, that world is enormously varied. And all of that variation comes not from the molecule, but from how the molecules are stacked. How many of them, how big the chunks are, how much air is mixed in, how thick the layer is. The arrangement is doing all the work. Now think about what that means for everything else. Carbon atoms, all by themselves, are nothing special. But arrange them one way, and you get coal. Arrange them another way, and you get pencil lead, which is graphite. Arrange them another way, and you get diamond. Arrange them yet another way, and you get the molecules of life. Same atom, totally different things, depending on arrangement. This is one of the deepest ideas in all of science. The richness of the world is not in the variety of the parts. The parts are simple, repetitive, almost boring. The richness is in the number of ways the parts can be put together. Snow versus ice is a tiny taste of that. Let me push this a little further, because I do not want you to walk away thinking this is just a cute fact about water. Have you ever wondered why your skin looks the way it does? Why blood is so red when you cut yourself, but veins look blue under the skin? Why some flowers are vivid and others are pale? Why the same paint can look matte or glossy depending on how you finish it? All of it comes back to this, to boundaries, to surfaces, to the way structures handle light. A pearl is made of the same calcium carbonate as a piece of chalk. But a pearl has its layers stacked at very specific thicknesses, and so it shines with that iridescent glow. Chalk does not. Same molecules, different arrangement. A butterfly's wing has no blue pigment in it, even when the butterfly looks an electric blue. The blue comes from microscopic ridges on the scales of the wing, ridges spaced just right to bounce blue light back. Crush the scales, the blue goes away. The chemistry never had blue in it. The structure had blue in it. There is a beetle in nature whose shell is whiter than any white you have ever seen, whiter even than fresh snow. And people have studied it carefully and they have found that it is a structural white. The beetle's shell has microscopic fibers arranged in a tangled random network, and that network scatters light at every wavelength. No pigment, no paint, just structure. Same trick as the snow, but optimized over millions of years of evolution to be even more efficient. Once you start to see this, you realize you have been living in an illusion all your life. You think the world is full of substances with their own colors. But really, the world is full of atoms that are mostly very simple, and the colors and textures and shines and matte finishes that you see are mostly stories told by the geometry, not by the atoms. Now let me bring you back to where we started, because I want to tie this off properly. You picked up an ice cube. You picked up a handful of snow. They are the same atoms. They look completely different. We have spent some time figuring out why, and the answer turns out to be deeper than just snow. The answer is that in the ice cube, light has only two boundaries to deal with, and so it sails through. In the snow, light has trillions of boundaries to deal with, and so it gets scattered back at you, in all directions and all colors equally, and you see white. But underneath that answer is something even more interesting. The interesting thing is that the world's appearance is not just chemistry. It is geometry. It is structure. It is arrangement. The same parts can build a window or build a snowfield, can build a transparent block or a brilliant white powder, can build a thing you see through or a thing you can barely look at. And this is something to think about the next time you look at the world. Are you seeing the substance, or are you seeing the structure? Most of the time, you are seeing the structure, and you do not even realize it. I will leave you with one last thought. There was a winter when I was much younger, and I remember walking through a field after a heavy snow had fallen. The snow was so bright that it hurt to look at, and I remember bending down and picking up a single tiny piece of it, holding it on my fingertip and watching it. And up close, that tiny grain, that single fragment, was not white at all. It was clear. It sparkled. It had the look of a piece of glass. I had spent my whole life thinking snow was white. But snow is not white. Snow is clear. We just see it as white because there are so many of them, and because each one bounces a little bit of the light back, and your eye, looking at the trillion of them, does not see any one. It sees the average. The average is white. I think that is a useful way to see almost everything in the world. The big appearance is an average over many, many small parts, and the small parts often do not look anything like the big appearance. The crowd is loud, but each person is quiet. The cloud is opaque, but each droplet is transparent. The snowfield is blinding, but each crystal is invisible. Once you start looking that way, the world becomes a much more interesting place. You start asking, what are the small parts really? What are they doing? What does the average look like, and how does it come from them? Sometimes the answer is surprising. Sometimes the answer is beautiful. And sometimes, like in our story today, the answer is both. So here is what I want to leave you with. Tonight, if you can, find a piece of clear plastic, a thin sheet of it, and rough up the surface with some sandpaper. You will turn a window into a frosted pane right in your hands. You will see a clear thing become a white thing in front of your eyes, and you will know exactly why. Or, if there is snow where you are, hold a single piece of it on your finger, up close, and look at it before it melts. Look at the clearness of it. Look at the transparency of one little bit of what you have always called white. Tell me which one you tried, and what you saw when you did it.